All right, so today you guys are going to be doing applications of exponential and logarithmic equations. The goal for today, which I realize I did not type in here, but I need to make sure that I include that. But the goal for today is that students will be able to apply properties of exponential and logarithmic equations or logarithmic functions to real world situations. That's your goal for today, okay? And so make sure you get that down as you're taking your notes. All right, and we're going to take a look at this very first problem because pretty much you have all the notes, you have all the skills that are needed in order to do these types of problems. Okay, and so we're just going to pretty much dive into it with some examples. You are going to do some with the video, like the video will work it out with you, and then I'm going to ask you to pause the video for the last a few examples, so that way you can try them on your own, and then you can check them with the answers. Okay. So the first one says the population A of t in thousands of a city is modeled by the function A of t equals 30e raised to the 0.02t, where t is a number in years after 2010. Use this model to answer the following 4 questions. Now, it is awesome when the problem actually gives you the equation, because that means that you don't have to create yourself. It's pretty much, okay, can you work with the equation and can you answer the questions that are being asked? So when it asks, what is the population of the city in 2010? Well, the equation was modeled to represent the number of years after 2010. So it's basically asking you for the initial population. So in 2010, that is the initial population. So the initial population basically means when t equals 0. So in order to figure out the value of, or the answer of A, you're pretty much going to plug in 0 for t. So that's going to be 30e raised to the 0.02 times 0. And we all know that anything raised to the 0 power is 1. So that's going to be 30e to the 0 power. So that's going to basically be 30 times 1, which is just 30. So that means that there are 30, not 30 people, but 30,000 people who are in the city in 2010, because it does say A of t is modeled in thousands. So not 30, but 30,000 people. Now for part B, it says, by what percentage is the population of the city increasing each year? So it's basically like, this is like one of those write down problems. It's actually asking you how fast is the population increasing? What is the rate? And that answer is right there in your equation in the exponent with the t. Okay, so that decimal represents the rate in which it's increasing, and so all you have to do is you have to take that number and then multiply it by 100 to actually get the percentage. So the percentage that is increasing is 2%. What would the population of the city be in 2020? Well, since the equation is modeled for the number of years after 2010, 2020 is 10 years later. So basically t equals 10, and so you're going to plug in 10 into your equation to figure out the population in 2020. So that's going to be 0.02 times 10. So that's going to be 30e raised to the um, 0.2. And you're basically going to plug that into your calculator. As you can estimate, these particular problems are going to be calculator based, because you are going to be dealing with things with exponentials. And so when you type it in around the 3 significant figures, you're going to get 36,600 people if you round to 3 significant figures. Now for D, it's asking, when will the city be 60,000? Okay, so 60,000 people. When will it happen? You're actually looking for t. You're actually looking for the number of years. Okay, and so in order to figure this out, you're basically going to take the 60,000, you're going to plug in for A of t. But you gotta be careful, because it says right here that A of t is in thousands. So when we go to plug in 60,000 in for A of t, we're not actually going to plug in 60,000, but we're going to plug in 60, because again, A of t is in thousands. So that's going to be 60 equals 30e raised to the 0.02t. And now we're going to use our skills of solving exponential equations in order to find the value of t. So if you guys recall, remember you start by dividing both sides by 30, because you got to get the base with the exponent by itself first. So we divide both sides by 30. That'll leave us with 2 equals e raised to the 0.02t. And anytime e is involved in a problem, we know that we're going to end up taking the ln of both sides because we have to basically get that, we have to get rid of that e. We got to bring that exponent down to the front, okay? Or we got to bring it down out of the exponent. So when we do that, we know we're going to have ln of 2, and the ln of e is equal to 1, so that cancels out. So you're left with 0.02t equals ln of 2. And so basically you'll end up dividing ln of 2 by 0.02 to find your value of t. And when you do that, you'll get that your time is about 34.7 years. So that's about 35 years later is when the population is going to be 60,000 people, or 2045. Okay, so basically, again, when the equation is given to you, you are basically trying to see, okay, can you decipher what the problem is actually asking you to do in order to solve these problems? So let's take a look at the next one. We're going to look at this one together, and then after this, you're going to be trying a few on your own. So it says a casserole is removed from the oven and cools according to the model with the equation T of t equals 85e raised to the negative 0.1 t, where t is the time in minutes, so t is in minutes, and capital T is the temperature in Celsius. So what is the temperature of the casserole when it's removed from the oven? Can you decipher what that means? That basically means that what is the initial temperature of the casserole? So we are going to plug in another 0 for t because, again, we're looking to see the initial time of the temperature when it was removed from the oven. So when you plug in 0, that would be 85e raised to the 0 power. And of course, we know that anything to the 0 power is 1. So that means it's going to be 85 degrees Celsius. And I am going to type this out because trying to go into the symbol system and pull out the actual symbols is going to be a little bit too much for me. So for B, it says, if the temperature of the room is 25 degrees Celsius, how long will it take for the casserole to reach room temperature? So again, this is another one where you are looking for the time. So you're going to be plugging in 25 degrees for the T of T, and then you're going to have 85e to the negative 0.01 T. And you have to go through this and solve. Now, yes, we can solve this algebraically. By dividing both sides by 85, taking the ln of both sides, just like how we did the last problem. But you know, you can also do this using your calculator. So I'm going to take advantage of this example and just refresh your memory how you can do it using your calculator. So once you get to this point, you'll plug 25 into y1 into your graphing calculator. So 25 into y1. And then you'll plug in the entire right side into y2, and basically you're looking to see where the two are going to equal each other, or where that time value when what am I trying to say? When the time value basically where they intersect. Okay, so at this point, you're going to plug 25 into y1 and then the right side into y2, and then you're going to graph it. Okay, now you might have to adjust your window so that way you can graph it. Okay, but you want to adjust your window so that you can see where the exponential curve and where the line of y equals 25 actually intersects. Okay, now for me, I'm going to use this application called Desmos, which allows me to graph these two curves, so I can at least show you a little bit of what your graph should somewhat look like. And as you see, they kind of intersect right here, a little bit after 10, maybe even a little bit after 12. Okay, but I'm looking for that intersection point right there. And as we can see, when I click on that intersection point, and what you would do is you would press the second button, the trace button, which takes you down the intersection, and then you would click enter 3 times, and it will pull up this exact same point. And you would see that, okay, so where the two curves intersect each other, or the time in which the temperature is going to be at 25 degrees Celsius, would be at 12.2 minutes if you rounded 3 significant figures. So our answer here is going to be T is about 12.2 minutes. Okay. If you wanted to include a little sketch of the graph of what that looks like, you could do that as well to kind of enforce the whole idea of, okay, I looked at the graph, because you never want to actually put in, y1, y2 um, into your work. Okay, so you want to show the line, y equals 25. It's a quick sketch. And then you want to show another line that represents your curve, and it's intersecting somewhere up here, and then hitting, and then we're looking for that value right there. Okay, you want to do something like this, and kind of make a note that this would be 85 on the y-axis, and so on and so forth. Okay, so that's how you could do that one. Again, we could have done it using the algebraic processes like how we did before, like the first example, but I wanted to show you how to do it also using your graphing calculator, and it works both ways every time. Okay, so from here I want you guys to pause the video. I actually want you to try and to work out the rest of these problems, and when you are ready to see the answer, press play, and then I'll walk you through everything. Okay, so pause the video, read this question, and try to work it out. If you got stuck, this can help you here. This formula is the formula for compound interest. You would have learned about this back in your Algebra 2 days, but it basically is the equation that you use to represent any type of problem that's being compounded annually, usually dealing with money. FV represents your future value, PV represents your present value, basically what you start with, and then you multiply by 1 plus R over K times 100, R being your rate. You literally plug in the rate as a percentage. K, the number of times a year is being compounded, and N is your time in years. Again, K is the number of times it's being compounded per year, and it usually tells you that in the problem. So if it says compounded annually, well, annually would equal the number 1, 1 year. If it said quarterly, quarterly would be 4. Monthly, 12 months in a year, so that'd be 12. Semi-annually would be 2, and so on and so forth. Okay, you would use this formula right here. However, you don't necessarily have to use this formula. You could have just used the fact that we are dealing with exponential equation, where the general form is a times b to the x. A represents what you start with, your starting value, and then b represents the rate. Okay, now it's very important. If you're talking about an increase, it's always 1 plus your rate. So this would be, if you're talking about increase, but then it would be 1 minus your rate if you were dealing with a decrease. So depending on the problem, since it says the sum of $450 is invested, clearly this would be, an increase because you are gaining money when you invest money, if you didn't know that. So you would do 1 plus your rate to help you out there, and then X, of course, would represent your time, and your time will be broken down into years. So either one works. And so let's take a look at the answers. I'm going to move this box here. And as you can see, they use the basic exponential way. You could have done it using the present value, the future value way, and you still would have gotten the exact same equation once you plugged everything in. Because it says to write down a formula for the value of the investment after n years. Well, you have 450 is what you started with, times 1.032. So, like I said, it would be 1 plus your rate. Clearly, your rate would be a decimal. And then you raise to the n power, or X represents your years. You would have gotten the same thing if you used this formula up here. So then for B, it asks you how many years will the first value exceed 600. This one's done algebraically. Let's start by dividing both sides, actually setting it greater than 600, dividing both sides by 450, taking the log of both sides and bringing down the exponent, dividing both sides by the log of 1.032, getting your decimal, which is 9.133, repeating. And so then the first year, how many years will it be before it exceeds $600? It wouldn't be 9 years, because at 9 years, you'd probably be just a little less than 600. So the answer would have been 10 years. Okay? Here's the next one. Pause the video and try to go ahead and solve this problem. And when you're ready to see the answer, press play. All right, so in the early stages of the measles epidemic, there were 100 people infected, and each day the number rose by 10%. Again, if the number rose by 10%, that means it's an increase. So hopefully you set it up as 1 plus your rate as a decimal. 100 people is what you started out with. So hopefully your equation kind of set up in this similar fashion, where you had 100 times 1.1 to the n power. And since it asks you how many people were affected after 2 days, you plug in 2 for n because it did say for each day the number rose by 10%. So basically your time would be turned into not years but into days. So you have 121 people. After a week, well, a week is 7 days, so you'll plug in 7 to get 195. Of course, you're rounding 3 significant figures because I'm almost certain that these were not whole numbers, and you can't really have a fraction of a person. Okay, so you got to make sure you round the correct way. And this is how long would it take for 250 people to be infected? Well, that means we would have set our equation equal to 250, as you can see there. And then again, it is solved algebraically. Divide both sides by 100, take the log of both sides and then divide. And so you have about 9.6 days, or 10 days would have been acceptable as well. Here's the next one. Pause it when you're ready to see the answer, and then or pause it when you're working on it, and press play when you're ready to see the answer. Forest fires spread exponentially. Every hour that the fire is left to burn unchecked, 15% of the remaining area is burned. Okay, so you got to be careful. This one, okay, it represents how much it is being burnt. Okay, and if it says if 10 hectares are burnt and the fire becomes out of control, how long will it take until 10,000 hectares are burning? So you start with your initial amount, which was 10 hectares. It is increasing at 15% every hour that's left unburnt. So it's going to be 1.15 raised to the n power because it represents every hour. So you're trying to figure out how long it will take before 10,000 hectares is burning. So there's your equation that you set up. You divide both sides by 10, and you take the log of both sides, bringing down the exponent, divide both sides, and it would take about 49.4 hours to burn. Here's the next one. Pause it, press play when you're ready. And if you're wondering, those are 9s right there. That's a 9 here, that's a 9 here. So 9 plus 29e raised to the negative 0.063t. All right, so you have to sketch a graph. So you actually had to sketch it, okay? Now, a sketch doesn't have to be too exact. You can use your calculator to help you. But the one thing definitely I can say that mark schemes are going to be looking for when you have a problem like this, the mark scheme is going to be looking to see if it crosses the y-axis at the correct point, if there's a horizontal asymptote that you're not touching that horizontal asymptote, and if there was a scale, if they told you that you had to draw to a particular scale, you had to follow the scale. Since you didn't have that, you pretty much just need to give it a sketch, y-intercept where it needs to be, asymptote where it needs to be. So you should have had this for part A, your sketch, okay? This one's a little bit more in detail, but as you can see, it does have a y-intercept that's in between 35 and 40, which is what you would get if you plugged in 0 for t. And you can kind of see that it's flattening out at your vertical asymptote. At your horizontal asymptote. So Joseph, he's doing a parachute jump for charity. We're trying to figure out what was Joseph's speed at the instant the parachute was open, aka the initial time. So you plug in 0 for t, and you work it out. So it's going to be miles per or meters per second. For C, what was his lowest possible speed if he fell from a very great height? Well, to do that, you basically start looking at the end behavior. Basically, the longer that the longer that the parachute is open is asking what's the lowest possible speed if he fell from a very great height. So basically, when he first jumps, he's falling out of the plane. All right, and they do not release. If you've ever seen anything about parachute jumping, they don't release the parachute right away. They fall for a little bit, they free fall for a little bit, and then they open up the parachute. So this right here is when they're free falling, they start to open up the parachute, and then they're going to start to level out to a consistent speed as they fall to the earth. Okay, so when it's asking you what was his lowest possible speed, basically when does he start to level out, aka you're approaching the horizontal asymptote. So as t gets really, really large, as time is moving on, as the seconds start moving on, and as he's starting to get a consistent speed, how fast is he going to be going? Well, he's going to basically level out at 9 meters per second. For D, if he actually landed after 45 seconds, what was his speed on the landing, okay? So we know he's going to level out and eventually he's going to end up hitting the ground. But it's actually, this problem wants to know, okay, if he landed after 45 seconds of jumping out of that plane, what was the speed when he landed? So you're basically going to plug in 45 for t. And so basically he's like falling at 10.7 meters per second if he hits the ground after 45 seconds based off of this model. So you basically you're plugging in 45 for t. And the last one, how long did it take him to reach half the speed he had when the parachute first opened? Well, we know when the parachute first opened, he was at 38 meters per second. So we're trying to figure out half of that speed he had when the parachute was open. Well, half of 38 is 19. So you're going to use that and you're going to plug 19 in for B. And you'll set basically the equation of 9 plus 29e raised to the negative 0.063t equal to 19 and solve out that equation. Subtract 9, divide by 29. And since we have e, you're going to take the ln of both sides. And when you take the ln of e, remember it cancels out. And then your last step is to divide by negative 0.063, which gives you about 16.9. So that basically tells us that 17 seconds was how long it took him to reach half the speed he had when the parachute was first open. All right, so for the last one, two variables x and n are connected by the formula x equals a, I forgot to include in the binary x in this problem, so I do apologize. Okay, so it says two variables x and n are connected by the formula x equals a times n to the b. When n is 2, x is 32, and when n is 3, x is 108. Find the values of a and b. So go ahead and pause the video, work it out to find the values of a and b. If you're stuck, did you at least plug in the values and realize that it is a system of two variables? And so you're going to use systems of equations to solve? That's my hint. Okay, so pause this video, don't go any forward, actually try to work it out now knowing that it's supposed to be a system. So since you know that it's a system, hopefully you set it up as 32 equals a times 2 to the b, and 108 equals a times 3 to the b. And then you solved by taking the ln of both sides. Because if you divided by a, you basically would have had a fraction that you would have taken the ln of, and eventually you would have ended back at the same point here. So if you took the ln of both sides, it would have been ln of 32 equals the ln of a plus b ln of 2. Because remember, when things are being multiplied and you apply the logarithm, you can expand them by addition. So that's one of your laws of logarithms. So then you have the same thing for equation 2, which says ln of 108 equals the ln of a plus b ln of 3. And so you can multiply, you get solve it simultaneously by multiplying the bottom equation by -1, basically subtracting. So then when you did that, you would have gotten the ln of 108 minus the ln of 32 equals b ln of 3 minus b ln of 2. You could factor out a b, of course. And then you would divide. And so b would equal the ln of 108 minus the ln of 32, all over the ln of 3 minus the ln of 2. And actually, this could have been done without a calculator because when you condense it, you would end up getting b equals 3 because you would divide 108 and 32, and then 3 and 2, and then basically you would end up just dividing them all together. And then once you find that b is equal to 3, you would plug it back into either equation 1 or equation 2. And so, for example, if I plugged into equation 1, it'll be 32 equals a times 2 cubed, which will basically be 8. So 32 equals 8a, divide both sides by 8, and a would equal 4. And so here are just a few problems that deal with the application process of using exponentials and logarithms. As you can see, we use our properties, we can use our steps to solving exponential equations here. And so that's pretty much the bulk of it. You guys are going to work on your homework now, and if you have any questions, please make sure that you message me on Schoology, or you can always get in touch with me other ways. All right? Have a good day, guys.